We are now going to look into specific cases that use the change of variable that we've talked about in our previous lesson, starting with exponentials. If you have an integral that involves an exponential, chances are that just by looking at it, you can break it down into these three parts. Actually two, because the e doesn't count. Well, the power of the e is going to be your new variable, so you have to differentiate mentally, and you will be able to find it as is, or a tiny variation of it that can be easily transformed into the thing itself, either by multiplying or dividing by a number. But you can find it within the overall expression. Okay? So let's say that you have 2x times e to the power of x squared. If you take x squared as being your variable, mentally differentiated, so that's 2x, and 2x is the thing that you have over here. Imagine that instead of 2x over here, you would have 4x. No problem. Just divide this by 2 as long as you multiply by 2 outside of the integral, and then you will have what you need. Okay? So what is the procedure? If it fits into that, your new variable is going to be the power, differentiated, so do du by dx, and it's going to be whatever the expression is. So du equals that expression times dx. Again, you'll have to find the new limits of integration. You already know how to do that. Substitute a on that function and get the new value c. Substitute b on that function and get the value d. And then this will turn into just e to the power of u. F dash of x times dx is du, so you put it there. And that's it. Okay? What if you have expressions of the form, and you have here what? You have a fraction. In the denominator, you have a function. And in the numerator, you have the derivative of that function. Or something that can be easily transformed into it, just like I explained in the example before. In that case, you pick the denominator to be your new variable, differentiate it, so du by dx is going to be another expression that should be this, or something very similar to that. So du is going to be that expression times dx. Find the new limits of integration, again by substituting x over here on the new function by a and b and getting the two values. And then when this is done, this will turn into just, don't forget, f of x is u, f dash of x times dx is just du, where is it over here? So it'll turn into this. And this is very simple to integrate. It's just natural logarithm of u between c and d. All right? Again, what are we doing here? We are still using the same method as we used before, but going directly to perform the operations that matter for each one of the situations. Trigonometric functions. You will have a simple mathematical expression that is going to be multiplied by either the sine or cosine of another mathematical expression. And the thing is that this one over here is the derivative of that, or again, something that can be very easily transformed into a derivative of that. So what do? You pick this as being your new variable. Du by dx is going to be this, or something very similar to that. Okay? So du equals this times dx. Get the new limits of integration using the same method, substituting a and b over there and getting c and d. So this is going to turn into the integral between the new limits of integration of the sine or the cosine of u du. Okay? Don't forget, du is this times that, which you can find here and here. All right? The result, obviously, is going to be, if you are using the sine, is minus cosine. If you are using the cosine, is the sine, but that you know already. What if you have the tan or the cotangent? Okay? Well, just use identities. You know that the tangent is sine over cosine of x. The cotangent is the other way around, is the cosine of x over the sine of x. And then these will fall into this category. if you think of it, what is sine? Sorry, it is the negative of the cosine differentiated. If you differentiate cosine, you have minus sine. If you multiply that by minus 1, you have sine. So in this case, you just have to multiply twice by minus 1, put a minus there, put a minus there, and this would turn into that, and then just fall into this category that we already explored a little while ago. This one is simpler because the cosine is the outcome of differentiating the sine. So it's more straightforward. You don't have to perform that tiny little operation before. Note that sometimes you'll have trigonometric functions that do not fall into this directly. So you may need to perform trigonometric identities so that it falls into one of these situations. On the other hand, if you have expressions of this form, you already learned in lesson 1 in this chapter where this comes from. Okay? You also have it also on MF 19. We talked about this. If you differentiate the tan of x, you'll have that, which means that if you integrate that, or more specifically, more broadly, 1 over x squared plus a squared, you'll get 1 over a tan negative 1 of x over a. So you have that in MF 19. You should just need to be aware that you may have these situations and know how to use it. So you just go ahead and apply that. What if you have fractions that seem complicated? Remember the previous chapter when I was talking about partial fractions, I mentioned in what situations that could be used. It could be used to do binomial expansion. That was the whole purpose of chapter 7. But I told you also that it could be used in integration, and this is it. So if you have a more complex fraction, try to perform partial fractions in it, and chances are that eventually each one of these fractions can be easily integrated, if not just by using this method over here.